Okay, so now I'm going to describe how I use this to validate 1.1.7. So this is the one where we want a set of 5 cards with 3 consecutive cards of the same rank. So the main challenge, right, so, well, just to point out, right, since it's a hand of cards and I think, order doesn't matter, then I'm using combinations. And I'm taking combinations from the numbers 0 through 51, and I'm taking them 5 at a time. But exactly which numbers they are won't actually end up mattering. So anyway, the basic idea behind how I determine whether or not a given hand, right, that's what this X is going to be, is it's basically going to be one instance of a hand, is I'm basically going to construct a dictionary of all of the numbers from 0 to 12 to be my representatives. And so a long time ago I said that there might be a reason why I'm talking about it like it's 0 to 12. Well, it's because it's somewhat easy to do it like that here. And so this is basically a map counting up how many of each face value occurs, right? So this is getting initialized with the keys 0 through 12, and each one is being initialized at value or count 0, and then I'm going to go through the hand and update the counts with each next card that I see. Okay, so for each card in the hand, right, card being some number from 0 to 51, I want to decide what its face value is. And so basically, 0 is going to be like a 2. And then 13, right? If you go 13 down, we might as well regard that as basically being like a 2 of the next suit. And then if you go 13 beyond that, you get a 2 of the next suit, and so on. So that effectively what the face value or rank of a card is basically just, right, all the cards of the same rank are going to compute to the same congruence mod 13. So that's what I do, right? So I take card mod 13, that's going to be one of my rank values from 0 to 12, and I increment, right, I bump it up by 1 for, right, I compute what its representative face value is and bump that count up by 1. If at any point I find that the counter reaches the number 3 for any face value, I return true right then and there because it's got at least 3 of some rank. And if I never get that, if that never happens, then at the end of everything I return false. It must never have reached any rank being 3. So that's how I define the triple. I generate all combinations using that property. I show a few of the instances, right? So what you would expect is, like, for instance, if you had 0 and 13 and 26 in the same hand, that would be 3 2s, right? And here again, 0 and 13 and 26. Now, what are the 3 things of the same face value here? I guess we've got a 1 and a 14, right? If you compute those mod 13, they all come out to 1. And then mod 13, so if you did 13, what, times 2? No, that's no good. Times 3, that's 39. That's too big. That's no good. But okay, here, right? 13 times 3 is 39. So 40 mod 13 is 1. And so, right, so you've got the 1, the 14, and the 40. Those are all representatives of a rank of 3 in the deck of cards. A little confusing perhaps, but in any case it works. And then just to check this one to make sure that this one makes sense, right? So I've got a 25, which is like an ace, right? Because 26 is 13 times 2, so that would have gotten me, right? So 26 is a 2, so if you go 1 back from that, you've got an ace. And then this is like 39, but back by 1, so that's another ace, basically. And then 13 times 3 is 39. So then what about 13 times 4? What is 13 times 4? not have to do this, but whatever. So 12, 1, 52. So do I have a 51 in here? Yes, I do. So that's the other ace. So anyway, so you can just see that, like, you know, by looking at exactly what the outputs are, you can confirm that it's actually counting the things that you want. I've just confirmed that it's getting me, in each instance, at least 3 things that all share the same rank. Now, at the end, because I told it to print the total that it returned here, then it counted up this many such cards. When I apply the formula that I found in the answer, which was this 13 times 4 choose 3, okay, 4 choose 3, just the same thing as 4, times 48 choose 2, I'm using the SimPy binomial function to compute that, and then plus 13 times 48, and it gets me the exact same answer. I indicated in that other video that there was another way by counting up with multiple, right, do this kind of like multiply counted method and then subtract off the multiple countings. And this confirms that that is also a valid way of doing it. So anyway, there is problem, right? That's the sort of confirmation of problem number 7. So let's maybe talk about problem number 8. So this one was what? We're getting 6 cards, 1 of every suit, right? So again, because it's hands of cards, I get a combination generator, cards numbered 0 to 51. I'm taking 6 at a time. And then the property of at least 1 of every suit, well, I get myself a suit counter, basically. Everything initialized at 0. And I go through the deck, and I basically segment the numbers in 13s, right? So every number from 0 to 12 is the first suit. It doesn't really matter which one I call it. And then 13 to 25 is the next suit, and so on. And so for every card, I determine what region it's in and increment the counter in the corresponding place. And then at the very end, once I'm done, I run through everything and say that if anything has a count of 0, return false, otherwise return true. And this generates the number you see here. And then when I compute the formula that I derived from my mathematical answer, you see that they come out to the same number. So it seems I got it right. Okay, on to problem number 9. So this one, right, I'm building words, right? So this time I'm actually going to use the Cartesian product, right? These are going to be words formed from the alphabet of 0 through 9. And I'm going to take them of length 5, right? And so if you give me a particular word, right? X is going to be a word, which is a list of digits 0 through 9. And I'm basically going to count up how many digits occur, right? So for each digit, find its count. And then I iterate through my input X, right? My word X. And for each one of them, it is a digit, and so I can really just immediately associate it with the index in count, or the key in count, sorry, increment it by 1, and every single time that I do this, I check to see whether or not it ever exceeds 2. If it does, I return false. If it never returns false, then ultimately it returns true. I get the output in this particular case of this number, and then when I compute my formula, and notice, by the way, that the easiest, or at least one easy way of getting a factorial in SimPy is to use the rising factorial, which I have as RF. And so it starts at 1, and I take 5 of them. So that's 1 times 2 times 3 times 4 times 5, so that's 5 factorial, right? And so I basically just compute my formula using all of these components, and it comes out to exactly the same number, so it turns out I got that one right also.